All right, in this segment we're going to be considering a second technique due to Rubin-Kelley for creating opportunities to apply superposition where none apparently exist. And this technique is called output voltage fixing. And we'll show it kind of in the abstract to begin with, just to give you the idea of what's going on. But suppose we have some linear circuit. And it's got maybe, let's say, an input voltage. And we would like to know the open circuited output voltage. And we're going to add a second source to this situation in a way that may strike you as kind of funny. We're actually going to take an auxiliary voltage source, Vout prime, and we're going to attach it to the output port. So we're going to fix the output voltage with this auxiliary voltage source. Okay, so when we attach the voltage source to the circuit, obviously we're forcing the voltage on the output of the circuit to be Vout prime. Right, this output voltage source that we've attached can supply an infinite amount of current, any current up to an infinite amount of current, to make the voltage across its terminals the specified value. And so it wins over the circuit. What the circuit does in protest is it will produce an output current that will have to be eaten by the output voltage source. So if the open circuited Vout, the circuit wants to be at Vout, happens to have been greater than Vout prime, then Iout is positive, so that when we disconnect the output voltage source, the tendency would be to increase the voltage across the output port. On the other hand, if Vout happened to be less than Vout prime, then Iout would actually be negative. It would be actually going in the opposite direction. The circuit would be pulling Vout, would be pulling Iout in to the circuit, so that when we let go with the output voltage source, it would have a tendency to reduce the voltage across this output port and try to restore it back to its original open circuited value. And if Vout prime happens to exactly equal Vout, then Iout equals 0. So when this test voltage source, or this auxiliary voltage source that we've attached, doesn't exchange any current with the circuit, at that particular value of voltage, that is the open circuited output voltage. Now you may wonder, why on earth are we doing this? It turns out that this is often a very easy way to do an analysis of a circuit, because it will allow us by superposition to break the circuit analysis problem up into simpler pieces. And because the output voltage is constrained, when we analyze those sub-problems, it turns out very often that makes the problem that we have to solve actually quite a lot easier. There might be some feedback, for instance, from the output back to some internal node in the circuit, like you might have in an op-amp circuit. And when we have the output voltage fixed, we're effectively disabling the feedback. And we wind up being able to analyze the circuit with a feedback loop disabled without ever having to analyze the full thing simultaneously, which is really quite a nice feature. Okay, so what we do is we attach our voltage source, and then the basic idea is we want to find the value of, so we want to find the value of V out, or the value of V out, yep, that makes I out equal to 0. And we can do that by superposition. So I out is a function of both V in and V out. And we're going to basically consider I out, it's actually because it's a linear circuit, I out is the sum of some component due to the input plus I out 2, which is a component due to V out. V out prime, let's say. And we will basically set the sum of two things equal to 0 and solve for the value that makes I out equal to 0. And so to do I out 1, we basically turn off the output voltage source. So I out 1 is computed with the output voltage source replaced by a short circuit. Like so. And so we do that first. So I out 1. And then we do I out 2 by replacing our output voltage source, say, and replacing the input with a short. So that'll be I out 2. And it turns out that I out 2 is just equal to V out, it's actually minus V out over R out, where R out is the resistance, the driving point resistance seen looking into the output port. So we can probe that here with an output voltage source, and strictly speaking we would be looking at the incremental output conductance, but that's 1 over the incremental output resistance. Now for our sign conventions, for something like a port resistance, it's positive current flowing into the positive terminal instead of out of, and that accounts for the minus sign here. Okay, so if we have I out 1 plus I out 2 equals 0, and we substitute in minus V out over R out in for I out 2, we have I out 1 minus V out over R out equals 0. We rearrange this and solve for V out. We find that V out equals basically I out 1 times R out. Okay, and that's the basic idea. So we're computing two things. We're breaking this output voltage up into two pieces. One is the output voltage, or rather the output current, computed due to the input voltage, the output voltage shorted out. And that current we then multiply by just the incremental output resistance, or rather the driving point output resistance of the circuit, computed with the input voltage source replaced by a short circuit. And so that may not make very much sense, but we'll do a couple of examples. One very simple example we've done a million times before now, which is just our two-way voltage divider. And we're going to compute the voltage, the output voltage, by this output voltage fixing technique. So here's our circuit, Vn. Here's our output voltage. R1, R2. We're going to apply our voltage source to the output. And we want to compute I out due to both of these things and find the value, that combination of these two things that make I out equal to 0. We're going to apply superposition, so we replace V out with a short. And basically, note that R2 is shorted out. And so, basically, I out 1, using our former nomenclature here, I out 1. So this is source 1. Source 2 is just Vn minus 0. This is ground here. The voltage, all of Vn appears across R1. So Vn over R1. R2 doesn't come in because it's shorted out, so there's no current flowing through it. All of the current, if you like, through R1 goes for the short circuit and bypasses R2. So now the other piece is R out. We replace Vn with a conceptually we replace Vn with a short circuit. We apply a test voltage source to the output, and we want to know what is I out 2. But what we saw in general was that if we think of the current as flowing back in, we can get the incremental, or we can get the driving point output conductance or the driving point output resistance with this arrangement, and we need to find basically R out. And if we can just look into this port and say, well, I see these two resistors connected in parallel with each other, so I know that the answer is basically R1 parallel R2. I can just get V out, the V out that makes I out equal to 0 as I out 1 times R out, which is equal to going to be R1 parallel R2 over R1, which of course we can simplify by expanding as product of the sum over the sum, and then the R1s cancel. So this is going to be equal to R2 over R1 plus R2. Okay, so that's a trivial example. You would never use this technique for this particular example. I just wanted to do it as a simple example just to give you an idea of what's going on. What I really want to do is apply this to our non-series parallel network that we used voltage source splitting on the other day. Okay, so our problem the other day is we had this voltage source, we had our ladder network, and we had this troublesome fifth resistor up here. And we want to know what is the voltage here. So we got R1, R2, R3, R4, and R5. And so now we're going to apply this idea of output voltage fixing. So we're going to apply our test voltage source to the output here. And this will be source 1 and source 2. And the idea is we replace this output voltage source with a short to get I out 1. Now, it turns out, and we can do this a couple of different ways. I guess we'll just do it directly. So we need to think our way through here. So we've got this node is basically shorted back to the negative terminal of Vn. And so all of Vn appears across R5. And I'm going to get some current flowing through R5, which is just I5, and that's going to be given by Vn over R5. I'm also going to have some current flowing through R1, call that I1. That current flows through R1. Some of it goes down here through R2. Some of it goes through here and goes to R3, and that's going to be I3. Okay. R4 is shorted out. Okay, so this current I3 goes through R3 and comes out over here, and it sees basically two places it can go. It could go through the R4, or it could go through the short. And it's all going to go for the short. Right? If you want to think of this as a two-way current divider, the conductance of the branch, or the current goes in proportion to the conductance of the branch we're talking about, and the short circuit has an infinite conductance. Compared to any finite conductance, it's going to get all of the current. So all of I3 is going to go this way. And so I out 1 is going to be basically I3 plus I5. So I out 1 is going to be, let's do the I5 component first. So that's just going to be Vn divided by R5. Plus, and now we have to do this component here, which is going to be the equivalent resistance of these three resistors, R1, R2, and R3. Okay, that's going to be Vn across that equivalent resistance. Again, R4 doesn't come in because it's basically shorted out. And so we get Vn divided by R1 in series with R2 parallel R3. And this is I1. So this is the amount of current that flows through R1. It's going to be, so this point is basically the same potential as that point. So R2 and R3 are in parallel with each other through this short circuit. R2 parallel R3 are in series with R1, and that's the equivalent resistance of this part of the network here. Okay? And so we need to know how much of that current goes through R3. And so we can multiply that by a current divider ratio, which is R2 parallel R3 over R3. We could, of course, also write this as the resistance of the opposite branch divided by the sum of the two resistances, which is what we would get if we expand this out as product over sum and cancel the R3s. So this is I3 over I1, this current divider ratio. And that's it. That's I out 1. And we can factor a V in out if we like, but we also need to know what is R out. So to get the R out piece, we basically replace the input with a short, and we say, well, what's R out? Conceptually, we've got this test voltage source, and we're applying a test voltage and looking at the current that flows back in and stuff like that. But very often we don't need to do that. We can, in point of fact, just do it by inspection, by just looking back in the network here. And this turns out to be one of those cases. We see R5 in parallel with this 4 resistor ladder network. We see R4 in parallel with R3 plus R1 in parallel with R2. So R out is equal to R5 in parallel with this equivalent resistance, which is R4 parallel R3 plus R1 parallel R2. And of course, because the parallel operator is associative, we can drop this outer set of parentheses if we like. That's a little bit of a simplification. And V out is just equal to V in times this thing, which is 1 over R5 plus, could say 1 over R3 times R2 parallel R3 over R1 plus R2 parallel R3. I was just slightly rearranging this and factoring out the V in, times R5 parallel R4 parallel R3 plus R1 parallel R2. I guess I need another set of parentheses. And this form is low entropy. It's nicely arranged in terms of series parallel combinations of resistors. It's also probably the simplest of the lot. Certainly a little bit simpler than the one we found from voltage source splitting and superposition. And it's definitely simpler than the one that we found in the notes through nodal analysis. So we'll be coming back to this technique. If we weren't able to do this output resistance, if we weren't able to write this down by effectively lumping things together in series parallel combinations, a good way of approaching the subpiece of this calculation is to use voltage source splitting on the output voltage source, and then look at the current flowing through all, say in this case, 3 wires or something like that. Now maybe that's a good thing to do. Let me do that. So we had here V out, and for R out, the sign convention is that I out goes back in. Okay. We leave source. We leave the input voltage source shorted out. And what we're going to do is we'd like to know what does I out do to V out. And we're going to use voltage source splitting and superposition on this sort of hierarchical piece of the calculation to break it up into further sub-pieces. Okay, and so we've got effectively three things connected to this output voltage source. We've got this part, R1, R2, and R3. We've got R5, and we've got R4. And so what we're going to do is we're going to split V out into three replica sources that are connected to each of these three pieces. And we'll call this 1, 2, and 3. But now the only difficulty is that our total output current, which used to be flowing through one wire, is now flowing through three different wires. We're interested in the total amount of current that's kind of flowing through this bundle of three wires. And in general, we could have a component of I out flowing in each wire due to its replica source, due to each of the three replica sources. So I out could have, in principle, 9 different components. And we typically will adopt sort of a double subscript notation where I out sub ij is the component of I out due to replica source j. Component of I out on branch I due to replica source j. Okay, so we're going to apply superposition, turning basically 2 of these 3 sources off by shorting them, by replacing them with shorts, and consider the components due to each of these sources in turn and superpose the results. So I out replacing, I guess in practice I should say that most of these n squared terms work out to be 0. And so while this may not seem like a good scaling law, n squared components or n squared subproblems, it turns out most of them are 0. So let's see how this works. So V out on branch 1 basically is just appearing across R4. Okay, and notice that this piece of the network, R1, R2, R3, it's shorted out here at the input. There's no voltage across it here. There's no current flowing in branch 2, and the same is true for R5. R5 is just shorted out. There's no current flowing in branch 3. So I out, there's no I out 2, 1, and there's no I out 3, 1. So the only thing we have is I out 1, 1, which is just trivially V out over R4. And this is basically I out 1, 1. And we're done with branch 1. So we shut this one off. And go up to branch 2 and put the V out back. Well, now branch 1 is shorted out, and there's no current flowing in branch 1 due to replica source 2. And branch 3 is still shorted out, so R5 is shorted, and there's no current flowing through branch 3. And so there's only one component due to replica source 2. And so there's a component of I out which is given by V out divided by the equivalent resistance of this branch. So we see R3 in series with R1 parallel R2. And this is I out 2, 2. And we're done. So we've considered 6 of the 9 components, and then we found only 2 of them are non-zero. We put branch 3 back. And we'll have a I out 3, 3, which is the current flowing through R5, but notice that this piece has no voltage across it, so there's no current flowing through branch 2. R4 is shorted out through this shorted out source, and we have no current flowing through branch 1, and so we just have an I out 3, 3, which is just V out over R5. Now, we're interested in R out, which is V out over I out. And notice how we get that. We factor the V out of this expression, right? So if we do that in place here, we're left with 1 times V out. And then when we to solve for V out over I out, we move the I out downstairs over here, and we move what's in brackets here downstairs over there, and we get 1 over this thing. Well, it's 1 over the sum of 1 over R4 plus 1 over R3 plus R1 parallel R2 plus 1 over R5. So it's 1 over the sum of a bunch of reciprocal resistances, which is just another way of saying the parallel combination of what's down in the denominators here. So that's just basically R4 parallel R3 plus R1 parallel R2 parallel R5. And so with a little bit of practice, you can basically go directly from this I out that we've accumulated directly to this R out. Okay, so if it weren't immediately apparent by just looking at this network that R5 was in parallel with R4 and that's in parallel with this thing, if that was not apparent from just inspection of the circuit schematic, an approach that is often very easy to do and allows us to break it into further subproblems that are all easier, much easier than the original, is to apply hierarchically this idea of voltage source splitting at the output port. Okay, so that's output voltage fixing, and that's it for this segment.